Hello there. My name is Ravi Bola. I'll be presenting a webinar on predicting castability of thin wall parts using simulations. The term castability in this context is really about being able to use simulations to determine when the metal freezes during the filling of the mold and to understand at what point defects are formed when we are making these extremely thin parts that are coming out. A little bit of a background of myself. I've dedicated about the past 18 years of my career in R&D in metal forming and casting technologies, with emphasis in high pressure die casting. And in 2012, I started Bholster Technologies, which is a consulting associate of Flow Science, and we provide simulation services and R&D support to anyone who wish to bring casting processes down to a science. For example, cooling design, cycle time, runner design, etc. And we specialize in automotive structural parts. For the background on this subject matter, I think many in the automotive world are already aware of the need to reduce the weight of cars. But even back in 1999, we can see reports published to look at the feasibility of casting very thin aluminum structures and replacing multi-piece stamped steel assembly into a single casting. And recently, there is renewed interest in casting these very thin parts because of the weight reduction requirements in the automotive industry, and in the consumer electronics world, looking to cast the housings out of metal instead of plastic. In this webinar, we'll be focused on looking at a case study of this part here, which is an example of a laptop case, which is 0.8 millimeters thick. And there is some researchers at the Korean Institute of Technology that did some extensive experimental work to determine what factors are required, what variables are required to successfully cast a part as thin as 0.8 millimeters thick using aluminum. A383 was the alloy they used. Background on this subject. The reason why there's so much interest and papers published on the feasibility of casting very thin parts, especially in high pressure die casting, is that these large thin wall parts are difficult to cast because the material freezes before it completely fills the die. The material's ability to flow and fill into a cavity before it freezes is termed fluidity. The fluidity is referred to as a property of a given alloy. There has been quite a bit of research on this subject. Two PhD theses on measuring the fluidity of aluminum alloys is cited at the very end of this webinar. And they basically conducted experiments in which they pour molten material into a mold made of ceramics, and you have this very special spiral here. And depending on how far the material travels, its fluidity is determined by the distance. Greater distance traveled, of course, greater fluidity. And the conclusion from both of these research basically said that greater superheat of the liquid metal will improve the fluidity, which is kind of obvious. Superheat is, of course, the temperature above the melting point. So if you have a higher temperature before you pour, it takes a lot longer before the material freezes. Silicon content is another variable. Higher silicon content improves fluidity for aluminum alloys. And this is interesting, but unfortunately, if we change the silicon content of a given alloy, especially for structural automotive, we're fundamentally changing the properties of this material, the mechanical properties, and perhaps defeat the purpose of the part, even though we have improved the fluidity. What we find interesting about the the conclusions from this work on fluidity measurements, even though it's qualitative and not directly usable, it demonstrates and it shows that the conditions in which fluidity is measured determine how far the material travels. For example, the conductivity of the mold temperature, and the insulating characteristics of this mold plays a significant role in how far the material travels. Unfortunately, these experiments are done under low pressure, and there is no direct correlation to conditions in high pressure die casting, where we were unable to find direct measurements on distance traveled or fluidity measurements to have a quantitative data that can determine or predict how far liquid metal will travel in a high pressure die casting die under those conditions. And that's what our real interest is. How can we know how far the material travels before it completely solidifies? And the problem in not being able to predict this is that when we design a very new part, especially if we push the limits of what has been known to be castable in high pressure die casting condition, we have a huge uncertainty at the design phase in terms of determining whether we can successfully make this part or not. For example, if you look at this concept here, in principle, we can always replace steel structures in a welded assembly into a single cast part, and we can even simulate it structurally to say that it is sound and suitable for the automotive application. But we do not have guarantees that if we put this in a die casting die, we can physically make it. Here is an example of the researchers at the Korean Institute of Technology, in which they have shown that various shot speed, of course, the faster your shot speed is, the more you can successfully cast this part. So there are different variables, and even for this gate design, this tangential gate design, they have concluded that they could not successfully cast this part, which we will have a detailed case study to compare with their experimental results, as you'll see later on in this presentation. Common simulation practice, which I've used in the past, and it's very valid for heavy wall casting such as transmission case, powertrain, components for high pressure die casting and engine blocks and the sorts. The standard approach is when the product design is complete, we have a gate design, we assume a temperature entering the biscuit, and we have some assumed die temperature simulation of the heat buildup, and then we run a simulation of the flow, and here's an example of what we'd look at. We see a uniform flow from the entrance of the part to the far end. It fills in a nice smooth way, and it vents at the overflows, therefore we should make a good part. And in principle, this is true from a trapped air perspective, that this gate design and this flow simulation shows that we should make a good casting, meaning that we won't have as much trapped air in the casting because of the uniform flow. But for thin wall parts, what happens is that when we use this exact approach, we end up building our die, and during the process development phase, it may take weeks or even months to learn how to cast the part and learn how to tweak the die temperature and shot speeds and furnace temperature, and it could be a very cumbersome and confusing process until we finally can be successful at casting these very thin parts. The goal of this work is to develop the ability to know ahead of time whether we can successfully make a brand new part, and to be able to predict this at the design phase, and even know, if we conclude we cannot make this part, to be able to determine what conditions are required to successfully make this part. So for the case of this 0.8 millimeter thick laptop cover, if our simulation can predict a physical defect, as you see here. So here's the flow simulation, tracking the heat loss, and when it freezes, it stops moving to demonstrate and show the exact mechanism and the probability region of where these cold flow defects can occur. That would give us the ability to either modify the design or change fundamentally the casting process or die temperature to be able to know ahead of time that we can predict that we can successfully cast this part without any surprises at the foundry. In order to be able to develop this capability, we went back to look at the fundamentals of what happens when a pool of liquid metal suddenly touches a steel surface. So in this condition, at time 0, in a perfect world, if we have liquid material suddenly touching a steel surface in which the surface is ideal, it's no contamination on the surface, the initial rate of heat transfer at time 0, the very moment it contacts that surface, the initial rate of heat transfer, the heat flux, would be infinite. And a very short time later, the surface, an incredibly short time later, the surface temperature increases of the steel, and the aluminum or the liquid metal in the vicinity of that surface decreases. And this reduction in temperature differential dramatically decreases that heat transfer. Here's an example in which we calculated the conduction across that interface for perfect contact. We can see it's very high, but within 1 or 2 milliseconds, that rate of heat transfer decreases because steel is not very conductive. You cannot remove the heat fast enough, and therefore that rate of heat transfer is dramatically reduced. Unfortunately, this initial, within the 1 or 2 milliseconds of contact, there is a tremendous of heat transfer that can occur to the steel that we need to account for when we're looking at very thin parts. Here is a simulation in which we have a 1 millimeter thick gap sandwiched between 2 steel blocks. And we can see after about 10 milliseconds, the heat that travels through the steel is only about 1/5 of a millimeter or so. And that is all, and the amount of heat transfer within that fraction of a millimeter in the die cavity surface is what determines or what controls that rate of heat transfer that either solidifies the material or not. So this is a simulation showing the trends of the surface heat up and the cooling of the part of the molten aluminum. In this case, it's A383 alloy. In real surfaces, however, we have a case in which, here's an example, steel surfaces that is typical surface finish for high pressure die casting die cavity is, it appears quite smooth, but if you look at the surface profile, which we've done in collaboration with the University of Toronto, we can see that we have measured the average roughness of these surfaces, and it's in the range of about 2 to 3 micrometers is the average RA value for this surface. And when surfaces that are imperfect come into contact, we have intermittent areas in which they come into contact, and that's where the majority of heat transfer occurs. And the air gap dramatically decreases the heat transfer in those areas. So in real surfaces we have at this interface in the thermal science community refers to the heat transfer or the uncertainty of heat transfer of this interface as an interfacial resistance. If you Google contact resistance or thermal contact resistance, you'll see an endless amount of research on this very subject for applications such as cooling of CPU chips and the likes to understand what controls that rate of heat transfer. In the high pressure die casting world, we don't use the term interfacial resistance, but we do use a heat transfer coefficient. They're basically the same thing. Heat transfer coefficient is simply 1 over that interface resistance. Solidification on contact with on real surfaces, then, if we look at the same scenario of molten metal suddenly contacting a surface at time 0, the only thing that controls that initial rate is the interface resistance that we see here. And that resistance is affected by the surface roughness and any contamination that's on the surface or of the steel or of the surface of the liquid material. We've done simulations for different heat transfer coefficients for this 1 millimeter thick slab. And we have noticed that, of course, the rate of solidification of this slab, say for the first 20 milliseconds in our simulation, which is in the order of fill times for parts of this sort, or less for that matter. And we can see that the amount of solidification that occurs dramatically varies depending on our choice of heat transfer coefficient at this interface. And if we look at the perception of what this heat transfer coefficient is in the high pressure die casting industry, we can see that reference from a value of about 5,000 to about 120,000 watts per meter squared K. So there's a wide variation of what we believe this number is. And if we are to ever stand a chance of being able to predict the solidification time within the time scales of a few milliseconds of very thin parts, we must have a very firm grasp on what this heat transfer coefficient is. So it turns out that the University of Toronto had faced a very similar challenge and a need to understand heat transfer coefficient. And the process that they were interested in is a thermal spray coating process in which you have a plasma torch and accelerating at a very high speed, sometimes at supersonic speed, onto a surface that we wish to coat. And they would inject powdered material, powdered ceramics or steel or whatever it is that they wish to coat. It melts and it collides with the surface and freezes very rapidly. The powder is in the order of micrometers in diameter, and the impact and solidification occurs within microseconds. So all that heat transfer, they were interested in looking at heat transfer within time scales of microseconds. And they've concluded that they must be able to measure that heat transfer coefficient at the surface. And one innovation they have developed was at a 40 nanosecond response time for a surface temperature sensor. And the techniques they use to measure this interface heat transfer coefficient is that imagine you have a steel surface here with that nanosecond response time thermocouple. If we deposit a liquid material onto this surface, the thermocouple measures the surface heat up. And that is the temperature increase of the steel surface itself. And the way they determine what the interface resistance must be is that they use an analytical conduction model in which the only unknown is the interface resistance. And by iteratively varying that interface resistance, when the curve matches the experimental data, they can back up what that thermal resistance is. And here's an example in which they simulated the impact of this droplet colliding with the surface. This is an actual simulation. This is actual photographs of the impact process, accounting for surface tension and things like that. In this case, there is no solidification in the simulation, but this is to confirm that the impact simulation was accurate. They then accounted for heat transfer, and they were able to predict the exact final splash shape of the droplets. And this entire event occurs within microseconds. And they were able to demonstrate that with the right heat transfer coefficient at the interface, they can predict the final shape of the splashes and be able to control the quality of this coating. We approach them to measure heat transfer coefficients for high pressure die casting dies. And what we have measured were heat transfer coefficient for various conditions in high pressure die casting die. So for H13 steel, we had the surface polished to a mirror finish, and we measure what that thermal resistance is. We then measure the increase in thermal resistance due to an increase in surface roughness, and this is an RA value of 3 micrometers, which is about the typical surface roughness for high pressure die casting die cavity surface. And we noticed that in the experiments and the measurements, die lube actually plays a significant role in increasing that interface resistance, as well as oxidation on the liquid metal surface. Also, if you actually sandblast your die cavity, we'll have an RA value of about 5 micrometers. And very interesting, that increases the interface resistance by about 25%. When we add up the contribution of all of this for a typical die casting cavity, not this roughened die, but the oxide film die lube and typical die cavity roughness, we end up with a heat transfer coefficient of 417,000 watts per meter squared K. We decided to use this to compare in our simulation and compare it with the experimental work from the researchers at the Korean Institute of Technology. And to very quickly outline their conclusion from their study, they have experimentally cast this part with a tangential gate and with what they refer to as a split type gating design, and have concluded that even with a shot speed of 4.5 meters per second, it wasn't possible to make a good casting with this tangential gate, but it is possible to make a sound casting with this gate. And this is the exact quote of their observation. Misruns and cracks were observed on specimens in the tangential gating system, while the split gate result in a sound casting with the highest injection speed of 4.5 meters per second. We've decided to simulate their exact conditions, and they've documented very clearly the conditions in which their experiments were conducted. We replicated this, and in our simulation we tested the sensitivity of heat transfer coefficient on predicting the cold flow defects, and we looked at the effect of shot speed on determining whether we can predict these cold flow defects, as well as we decided to look at even the effect of shot position, because as you'll see later on, whether you pre-fill a cavity or not dramatically affects the quality of the casting. But in our simulation, we made sure we did not make any assumptions, as may be done, is to assume the temperature entering the biscuit, but we actually simulated the pouring from the furnace temperature, tracked the heat loss in the shot sleeve, as well as the heat loss during the slow and the fast shot, so that we're not putting any assumptions in our simulation. We're trusting the models of the simulation with this heat transfer coefficient to see what kind of correlation we can obtain. Here are the results in which this is a simulation in which the pouring occurs within 3 seconds, and initially the temperature was 670 Celsius, and we can see there are local areas within the shot sleeve of the metal, whereas it's in the range of 570 Celsius, so you can have as much as 100 degrees Celsius drop in temperature just from pouring. And in the slow shot, it reduces, but not quite as much. From 600, we have temperature drops, and the actual temperature entering the biscuit is actually around 590 Celsius, even though the furnace and pour temperature is 670. So there's quite a bit of a difference there in what the temperature is that actually enters the runner system. Here's an animation of it to show that heat loss and the progressive heat loss, and the actual temperature going into the cavity is surprisingly much lower than what the furnace temperature is. So just from this, actually, it is interesting to note that if we're getting cold flow defects in any kind of casting processes, one thing we can pay attention to is to decrease the amount of time we pour into the shot sleeve, and even put thermocouples in the shot sleeve to measure what that temperature is, because it might be a lot colder than we might have expected. We then continue that simulation at a shot speed of 2.2 meters per second with our measured heat transfer coefficient. And we, of course, predicted visible defects in the part. And here is an example where we've seen this movie before, but the material splashes, totally freezes, stops moving, and then we have this kinds of defects. The results of this simulation compares very well with the experimental data in that it proves that at 2.2 meters per second we cannot make a good casting. Here are correlations of the actual casting to what we can see in the simulations, and we can see a very similar kind of a trend of what the casting looks like for the same range of shot speed. If we repeated this exact simulation with even the highest heat transfer coefficient known in the industry, it still predicts that the material will not freeze and predict that we will make a good casting at this speed of 2.2 meters per second. This, of course, contradicts the findings of the experiment and further confirms that a heat transfer coefficient higher than 120,000 watts per meter squared K is necessary to be able to predict the rapid heat loss that actually happens in the high pressure die casting foundry. And yeah, here's a simulation. We started the fast shot very early to make sure we don't have any prefill. Even though the flow is not perfect, in terms of trapped air, what we're interested in this study is to look and see that we do not have any freezing of the material. The material does not completely freeze before the cavity is filled, and therefore we can get a good casting. We were a little surprised that the tangential gate at 4.5 meters per second could not make a good casting. We ran the simulation and started the fast shot position, the typical time. Of course, for typical standard high pressure die casting process, we start the fast shot when the runner is totally full, then we go to fast shot when the metal goes into the cavity. And what we found with the tangential gate is that the shape and geometry of the gate is designed so that it always introduces material into the cavity before filling the runner, and therefore we always get a pre-fill condition, and that is the reason why it's not possible to make a good casting with the tangential gate. So here is an example. The material goes up the runner and is just by the angle and shape of the runner, it goes directly into the cavity, causing the material to freeze over. And this freezes over, pre-fills the cavity, causes the material to freeze. And by the time we hit the fast shot, it's too late. The material is frozen over. We cannot make a good casting. That can be seen here. So this simulation actually explains why this gate is not well suited to make a good casting, which also is in agreement with the findings. Here we have the split type gating in which their conclusion was that it's possible to make a good casting. We simulated this, and if we look at the animation, we can see that the geometry of the gate with these discrete feed runner branches or feed branches makes it such that most of the material fills the runner before it fills the part, and it doesn't have this tendency of pre-filling the part nearly as much, and therefore it's possible to fill the cavity without having the solidification, and therefore making a good casting. So what this is actually showing is that we have to be very careful in designing the runner system to not introduce material into the cavity during the slow shot and intermediate shot, some of you call this, before the fast shot. We're fully in the fast shot, and only then we can make a good casting. And one interesting thing we have observed from this is that the far end of this branch that we see here scoops some of the material and tries to direct it into the cavity. So further improvement of this gating design would be to put a bigger radius at this interface here. And therefore we won't be scooping that material, and even make this runner design and gating system more robust and less sensitive to shot position. We repeated the simulation with the tangential gate, but instead we start the fast shot very early. We started when the material is about at this point in the runner system, and it predicts that the material will not freeze over. And I think many of you in the making very thin structural automotive parts have already found out, perhaps through experiments, that you absolutely cannot have any prefill if you are to make a quality casting. Here we show that if you start the fast shot position very early, then the material is introduced into the cavity rapidly, and therefore will not have the cold flow defects that we've seen earlier. But of course, the disadvantage of starting a fast shot too early is that we'll have a lot more trapped gas and gas porosity unless we have a very effective vacuum and venting system. So so just to summarize what we've observed from this this work is that we found that there's a significant amount of heat loss that occurs during the pouring. So if we're having any kinds of cold flow defects, one thing to pay attention to is the method and duration of pour into the shot sleeve. I've always believed that the slow shot phase is one part of the process that has a huge amount of heat loss, but it turns out that heat loss during the slow shot phase is not nearly as much as during the pour phase. And this is, when you think about it, when we're pouring into the shot sleeve, it's already preheating the shot sleeve and having rapid convective heat transfer, which is why it drops in temperature so rapidly. And by the time we start the slow shot, the sleeve is already hot and the material does not move around as rapidly as during the pouring phase, and therefore does not lose as much heat. And of course, rapid heat is lost. Rapid heat loss occurs when the melt fills into the thin wall cavity, and of course this is due to a large ratio of die surface area to the small volume of molten material. And as we've seen, a very high heat transfer coefficient of 417,000 watts per meter squared K allowed us to specify and determine what shot speed, furnace temperature, die temperature, and even shot position is required to successfully make a good casting. And of course, we correctly predicted that we cannot make casting at 2.2 meters per second, and we correctly predicted we can at 4.5 meters per second, and determined that with the tangential gate, it's possible to make a good casting at this same speed. but if we start the fast shot position much earlier. So the conclusion is clear that this accurate measurement of 417,000 watts per meter squared K was necessary, was absolutely required in order to be able to have simulation able to predict these cold flow defects. Just a word of caution for those of you who would be interested in trying this is that this is the moment liquid metal touches the surface. The minute the material changes phase into a solid, the heat transfer coefficient at the interface will dramatically decrease to the order of about 2,000, and that's based on measurements that we have looked at as well. The precision of these predictions can further be improved through additional research like measuring the thermal resistance of the die loop for every casting condition, because it turns out that the thermal resistance of die loop varies significantly based on die loop type as well as concentration. And as you run a die casting die for a long time, its surface gets a little darker, and that may be due to oxide layer, and we have not measured the thermal resistance of that layer, and that may be a factor that could help us improve the precision of these predictions. But for those of you who are looking for practical application of this finding, one thing is, rather than wait for researchers to invent alloys with greater fluidity, we can focus on actually looking at the foundry conditions that affect fluidity and control those. And some of the thoughts that I've had that seems clear that came out of this research was that if you roughen the die cavity, you can have the material travel farther before it completely freezes over. And of course, you use die loop. There are some die loops that are very insulating. That can dramatically improve your success in casting very thin parts, as well as increase the loop concentration. So a richer die loop will, of course, be more insulating because it deposits a thicker thermal barrier onto the surface. And of course, as we've seen, designing runners to prevent the melt from entering the part during slow shot is critical in making these casting. And a few other areas that may be useful to be able to predict, to be able to physically cast very thin parts, is to actually make the steel, the mold out of a much lower conductivity steel. An area of research that may be valuable, as well as looking at coating insulating layers onto the cavity so that we have a thermal barrier that can make the material more fluid. And here's another very quick example of there's a brand new part, and we were looking at which gating system would be good at filling this very thin wall part. And we haven't completed this study, but I'm just showing you a quick evolution of runner design and why we had to make some changes to be able to decrease the kind of cold flow defects that occur. We simply model a runner design and gating system, and we find that for this design, the material travels up the biscuit very quickly and fills the center of the part, and it actually starts to freeze over. When it gets a dark blue, it's already frozen. This is Solifont was the alloy used in this study. And by the time we hit the fast shot, which the assumption would be that when you do the volume calculation, the fast shot occurs when the runner is filled. But the shape of the runner, the material doesn't know that it should fill the runner before the part. And if the geometry of the runner is such that it fills the part, it will not perform well, as we see here. We change the center branch to have this Y, to have a delay going to the center branch, and also have a little stagger into the feet of the center gate. And we can see that we can have a more balanced filling. Material fills the middle as well as the two sides, so we actually got it very right. One thing we saw here was that this branch scoops material into itself very quickly, and one way of changing that is to just change the radius of this corner. And but we can see an improvement of the simulation. So it's actually heat loss during filling, and pre-fill is the reason why we need to get the timing of all the gates to be as balanced as possible. And here is closer to the final design that we have. Not ideal, but the material did not freeze during the filling of this part. Here is a list of references. If you are interested, I can email this to you on the subject of fluidity. And that concludes my presentation. If you have any questions, feel free to contact myself or contact Flow Science, Dave Souders, at the email address shown below. And I am open to answering any questions that you may have.
Thanks, Robbie. So as Robbie said, we are going to open it up for questions. You have a few ways that you can ask questions today. Within the control panel, there is a text box. If you click within the text box, type your question in and hit submit, we'll get it in on our end. The next thing that you can do is you have a little hand icon in your control panel. You can click that little hand icon and we can go ahead and unmute you. Again, this only works if you are calling in on a phone or if you have a microphone set up. Last but not least, please write down Robbie's email address and you can contact him with any questions you might have in the future about anything related to this presentation. Please make sure that you indicate that you're part of this presentation so that he knows where this is coming from. You can also email us at webinars, plural, at diecasting.org. And if you can't get a hold of him for some reason, we will get a hold of him for you and you can get those questions over to him. So with that, I'm going to leave it open for a few minutes and see if any questions come through. Somebody did asked if they could have the presentation. So typically what happens is in order to have a copy of the PDF, you have to purchase the course through the NADCA's online education system and it's available there. Contacting the presenter separately is, that's up to him, his discretion. So if he is willing to give that out to you, then you can contact him about that. And so that answers that question. And so any other technical questions that you guys have, please send those in now. We're going to hang out on the line for a few minutes and see if anything comes in.
Well, it doesn't seem like we're getting too many questions, but you see the contact information here. You can either contact myself. Oh, here we have a question. The question here is, how do these rules apply to magnesium? The rule actually applies to magnesium in exactly the same way. Because the reason is that in the simulation, the properties of the material that determines its fluidity are the heat transfer coefficient that you've seen here, the density, the heat capacity, and thermal diffusivity of the material, which is all known. And therefore, by simply entering the alloy in the software, along with this heat transfer coefficient, you will have the ability to predict fluidity for any alloy in which you understand, in which you know this property. The other question we have is, where does Bholster Tech work out for consulting? We're based out of Toronto, Ontario, and of course, thanks to the internet, we can pretty much work with anyone who has internet access. Oh, yeah, I just needed to correct one thing in the contact information here. Forgive me. It's if you want to contact Flow3D or access their site, it's flow3d.com. Please forgive me for that.
You should see another question that has come through. You have a couple questions actually. One is from Earl and it says, how long does it take to properly design a runner gating system?
Okay. Yeah, well, it's an iteration, uh, something like that. For example, the very last example of that structural casting that I've cited, that took about a week to come up with three iterations of runner design and simulation. It takes approximately a week or a week and a half, about a day or two to run the simulation, and depending on how efficient the CAD designers are, my CAD designer was able to get each runner design completed within a day or so. So within three iterations, we were able to get nearly a finalized design within a week or a week and a half. Question on which software is used. We use Flow3D, and that's made from the software company Flow Science, based out of New Mexico, and you can contact them at the information shown on this final slide there.
I don't see any other questions coming through. I'm going to give everybody just a few seconds here. If you are currently in the process of typing a question in, if you could click that little hand icon, that's just going to let me know that you're typing and not to end prematurely.
Okay. And for anyone who may have questions later on, if you get a copy of my email address, rabbi@bholstertech.ca, feel free to send me a question anytime or request any information to clarify anything about this topic.
Okay, I don't see anything else coming in. So with that, Robbie, thank you for presenting today, and everybody else, thank you for attending, and we look forward to seeing you guys all on another webinar. Thanks, guys. Have a good day. Bye.
Thank you all. Bye-bye.